I just thought we'd finish off the differentiation from last week by looking at increasing and decreasing functions. If you weren't here for last week, it's not a big problem, and then we'll look at integration. Now, fortunately, although it's the last part of the topic, increasing and decreasing functions is very straightforward. It's very much common sense. An increasing function is one that's getting bigger. That means the gradient is positive. That's all it means. It's getting bigger, so the gradient must be positive. So the differential is greater than naught. So as soon as you get a question that mentions an increasing function, you put dy by dx is greater than naught, and the decreasing function is getting smaller, so the gradient is negative, so dy by dx is less than naught. If a function is neither increasing nor decreasing, it is, as we discussed last week, a stationary point. So, given this function, given y equals x cubed minus 6x squared minus 15x plus 5, find the range of values for which the function is increasing. So, how we do it? Well, first of all, tell the examiner what your thoughts are. If it's increasing, dy by dx is greater than naught.
Mr. Bentley,
Yes.
I think it's frozen. I'm just looking at a lined piece of paper.
Oh, hang on a minute. Well, why? Let's. Wait a minute. Why is that?
Very sorry, everyone.
No, I haven't pressed. Let me just try this. I'll have to share something else. Try a different route. If I just go back to there, stop sharing. Try share the camera. How's that?
Right. That seems to be okay, yeah.
Right. So if it is increasing, dy by dx is greater than naught. So you tell the examiner that, and now obviously start with what you're given. Y equals x cubed minus 6x squared minus 15x plus 25, and straight away you're going to get a mark for knowing that we're differentiating 3x squared minus 12x minus 15. Okay? And now this is why it's a favourite question towards the end of the paper, because it's going to test more than one topic. If increasing, three x squared minus 12x minus 15 is greater than naught. Therefore, solve that inequality. Now, for me, I tend to look for the critical values. The critical values are when that equals naught. And solving the quadratic, I'm not going to make a big fuss about this. X minus 5, x plus 1 equals naught, x equals 5, or x equals minus 1. Now then, that gives us our points where the gradient is naught. We want to know when the gradient is more than naught. Now I always tend to do this via a little table. Okay? X is minus 1, x is 5, and dy by dx The gradient is naught at those points. So what I want to do now is pick a value for x that's less than -1. Let's call it -2. So if I get a red pen or a different colour pen, if x equals -2, dy by dx is up here. I substitute -2 into that. And that would be x equals -2, dy by dx is -2 squared is 4, 3 4s are 12, plus 24, plus 25. In other words, that is positive. Dy by dx is positive. I don't need to know what it is, so long as that is more than... oh, wait a minute. I've just gone wrong here. It's -15, but anyway, it's still positive. Right? So, the gradient is positive for values of x less than -1. I now pick a value between -1 and 5, which is 0. Put x equals 0 into dy by dx, and you can see it's -15, which is negative. I don't need to know the values, I need to know that it is negative. And finally, I pick a number bigger than 5. So if x equals 6, dy by dx is, well, when you think about it, it doesn't take a lot of working. 6 squared is 36, 3 36s are 108. 6 12s are 72. That is going to be positive. So the gradient is positive for values of x less than -1 or more than 5. So it's increasing x is less than -1 or x is greater than 5. You'll notice, of course, you cannot write that as a single inequality. One of the most common errors I see on this sort of inequality question is people trying to combine that into one equality. If you've got a region that's less than that or more than that, it's two inequalities. If you get the region that's between those 2 points, you can do that as a single inequality. Okay? So, increasing, decreasing functions. It's the end of the topic of differentiation. Okay? It is quite popular because the examiners do like you to, or do like to put these questions that require 2 techniques in. Okay? Worth practicing. It's on all the practice stuff, it's on all the documentation from last lesson. Now, today, integration. Now, here's there are issues with integration. Your biggest issue is that your teacher will probably have raced through it. They'll have spent hours and hours and hours on differentiation, and then they'll have said something like, well, integration is the opposite, right? So they'll give you something like this. It's the opposite of differentiation. Now, it's just like division is the opposite of multiplication. And here's something to think about. Pretty much every number you can multiply by 7. Most numbers won't divide by 7. We have to do things like decimals and round them off, or fractions, or all sorts of things. It's the same with calculus. Pretty much everything will differentiate. A lot of functions will not integrate. We have to learn tricks and so on. So integration is always going to be a little bit more problematic. It's not difficult, it's, so long as you're appreciating there are going to be problems there. So in algebra, if f of x is x to the power of n, Now I'm taking a big leap here about opposite of differentiation is integration. This is revision, so you should be familiar with the integral sign. The integral of the function is x to the power of n plus 1 divided by n plus 1. Or, as probably you know, you increase the power by 1 and divide the coefficient by the new power. Now, we're going to look at, for a start, indefinite integration. And perversely, I'm going to start by differentiating. Hang on a minute. There's a mistake on this question here. I'm going to change this. I've made a mistake. If I just make that minus 12, rather than, we did the same thing twice. If I differentiate this, I would get 18x squared plus minus 18x. And if I was to differentiate this, I would get 18x squared minus 18x. You'll notice when you differentiate, the constants or the numbers disappear. Now, if integration undoes differentiation, the integral of that could be that or that. We don't know which one it would be. In fact, it is 6x cubed minus 9x squared plus or minus anything at all, depending on what we got. So it's called the indefinite integral. If you're simply asked to integrate a function, you work out the algebraic terms and then add a number. And it's called the indefinite integral because we don't know for definite what it is. Right? Always remember the constant when you integrate. Okay? Now, here's a function to integrate. Now, a couple of things about the notation. We're integrating the whole thing with respect to x. In year 12, you could get away with just writing that, the integral of that bit. But trust me, when you get to year 13, this bit here is very important. So the questions are going to be written like that. And if you're not used to writing them, you see the brackets, you think, oh, what do the brackets mean? Nothing. We're just integrating this thing. And the rules are pretty much as for differentiation. Okay? So, first job is to write the function with indices rather than square roots and fractional powers. So I've now got, it's the integral, because I've not integrated yet, so I'm going to integrate. And the thing I integrate always goes in brackets, 8x cubed minus 2x to the minus half plus 5x to the minus 2 dx. So it still says, the question's asked me to integrate. Here I'm saying I haven't integrated yet, I'm going to integrate it, and I put it in a form that I can integrate. And now, be very careful. A lot of people then sort of get halfway through and start differentiating. So we've now got, and the trick is, just calm down a bit and put an extra line in. It's 8x to the power of 4 divided by the new power, which is 4, minus 2x, now be careful, minus a half plus 1 is to the power of a half divided by a half, plus 5x, now be careful, minus 1 add 1, sorry, minus 2 add 1 is minus 1 divided by minus 1. So there's signs in here, there's fractions, all sorts of things that you don't like, which gives me 2x to the power of 4 minus, be careful, 4x to the half minus 5x to the minus 1. And you can, if you like, oh, sorry, and I've forgotten the plus c already, plus c. You can, if you like, leave it like that, or you could put it back into 2x to the power of 4 plus 4 root x minus 5 over x plus c. It's entirely up to you. Okay? So what I thought we'd do next is integrate a slightly more complex function. And it's the same as differentiation. We do all the donkey work before we integrate. So it's the integral of. Now, with these fractional ones, because you've got a single term in the denominator at the bottom, we can just divide the whole thing by root x. But notice the top has a bracket that needs expanding. So it's a bit like eating an elephant, this. How would you eat an elephant? One slice at a time. You set off at the beginning, you think, oh my God, I'll never eat the whole elephant. Slice it up, in enough slices, and eventually you will eat the elephant. So don't try and do too much in one go. My first job is to expand the top. Now you might want to put the face method or FOIL or whatever it is. You might know the shortcut. If you know the shortcut, it becomes 25x squared minus 30x plus 9 all over root x dx. I still haven't integrated, and I still can't integrate. Now, next job is to divide by root x. That is x to the power of a half. Okay? So all I've got to do is divide each one of these by x to the power of a half. So I've now got the integral of 25x. Now, 2 minus a half is 1.5. But we tend to write them as top-heavy fractions. 3 over 2, you'll see why in a minute. So it's 25x to the power of 3 over 2 minus 30x. Now that's the power of 1 divided by root x is the power of a half plus 9x to the power of minus a half, because it's x to the power of 0 minus a half, and we're integrating the whole thing with
You've
respect.
dropped your 9, Mr. Bentley.
I've dropped my 9. Yes, sorry. 9. It's quite easy to. That's what I mean about you've got to be. Just keep your wits and be careful and calm down. Yes. So now we're at a stage where we can integrate. It's awkward because you've got fractions in there. Just don't panic. For goodness sake, don't panic. So that is 25. Increase the power by 1. So it's x to the power of 5 over 2 divided by 5 over 2. Yeah? Minus 30x, increase the power by 1, it's 3 over 2, and divide by 3 over 2. Plus 9x, now minus a half plus 1 is plus a half, and divide that by a half plus c. And then simply do the divisions. Now, if you're struggling at this point, you've got a calculator. If you're not confident with fractions, which you probably won't be, as you won't be as competent as you should be, then it's fine. Use your calculator, but that would get you to 10x to the power of 5 over 2 minus 20x to the power of 3 over 2 plus 18x to the power of a half plus c. If you're not asked to do anything else with it, you could leave it like that, right? There are lots of ways of factorizing that you might see. To be honest, if you're not told to give it in any particular form, the less you do to something, the more chance you've got of not losing accuracy marks at the end. Okay? You could factorise out the 2 from that. You could factorise 2 root x from that, if you really wanted. So you'd have 2x to the half, 5x to the power of 3 over 2 minus 10x to the power of half plus 9. There's lots of things you can do. You know what? I'm going to leave well alone. You'll notice when you download the solutions later on, I've actually gone for an extra line. I'm not interested. So basically, can you integrate functions? Remember the constant. Now then, I know when this was introduced to me, it was like, but I don't like a constant, I want an answer. 2 add 2 is 4, there's an answer. Well, if integration is going to be any use, right, there may well be something in the question that allows us to find a constant. Okay? Now this is a case in point. The gradient of a curve is given by the function, and the curve passes through the point minus 3, 5. Find the equation of the curve. Well, the equation of the curve is y equals. Where do you start? Well, you start every question at exactly the same point. What are you given? dy by dx equals x brackets x plus 3 over x cubed. And actually, simply writing that down we feel we've made a start to the question. We've got pen on paper, you've made a start. Can you differentiate, can you integrate that as it stands? No. Why not? It's got brackets. So, expand the brackets. dy by dx is x squared plus 3 over x squared. Well, I'm going to just save a little bit of time and write 3x to the minus 2. Okay? And all I've done is I've taken a line out. Happy to take a line out? If you're not happy, put it in and do it again. Can you now integrate it? Yes. Because y is the integral of that. So using our notations we're happy with, y equals x cubed over 3. And again, it's awkward, just like division's awkward. There's quite often fractions in there. Don't panic. Plus 3x to the minus 1 divided by minus 1 plus c. And then, if it was me, if I'm going to be using it, I would say 3 equals x cubed over 3 minus 3 over x plus c. And it's still got the indefinite integral. We've got that plus c in there. Now, I left a bit of room to do this, but I'll do it alongside. So our notes look. Now, when you get to there, have you answered the question? No, because we haven't got the equation of the curve. We've got a constant in there. We've introduced that, but go back and read the question. At this point here, x equals minus 3 and y equals 5. So it's given me a connection between x and y. So if x equals minus 3, y equals 5. If I substitute those two values into that, I've got a y, I've got the x's, it will tell me what c is. So 5 equals minus 3 cubed over 3 minus 3 over minus 3 plus c. 5 equals, well, minus 3 cubed is minus 27, divided by 3 is minus 9. Minus 9. Minus 3 divided by minus 3 is plus 1, plus c. Move those over, c equals 13. Therefore, my equation is y equals x cubed over 3 minus 3 over x plus 13. And it doesn't matter which format you've used. You could have used that format, look, you could have said x cubed over 3 plus 3, x minus 1 over minus 1. It doesn't matter. So long as your answer means that, you'll see on the mark scheme, the magic words OE, or equivalent, or anything that means that. So it's not witchcraft, it's not magic, okay? It is simple techniques. Now, we're not going to finish integration today, but it doesn't bother me because we will continue with integration next lesson. I'm going to show you one more example before I show you where there is some practice work to do. And this is the definite integral. Now, let's just make one thing quite clear to you. On your calculator, you do have a button that looks like this. Right? You can use this to get to the right answer. So using that function and the X button, if you're careful about the way you program it, you can type that into your calculator using the up, down, left, right, and X button and roots and powers and parentheses. It's a bit awkward, but if you get used to it, it's a process you've probably got sorted. If you were in England, if you were asked that question, typed it into your calculator and pressed equal and wrote the answer down there, you'd get full marks. But you're not in England, you're in Wales. Right or wrong, like it or lump it, there's no point arguing. If you look at the front of your exam paper, it will say sufficient working must be seen to show the algebraic method you have used. That's not to say you can't check your final answer using your calculator, and I would recommend you did so. Okay? Now, the definite integral. Well, basically, this here tells me, again, it's what you're going to see in a textbook. The question, there's a function between two values, they're called limits, right, equals g of x, with those limits in, and then that. Let's translate it. There's the question. When you integrate f of x, it becomes something else, so we call it a different letter, g of x. And the two limits says all you got to do is put the b value into the function minus the a value into the function, and then you'll get a numerical answer. Now, obviously, when your maths teacher started teaching you this, it was an academic exercise to get a number. You're probably aware of what that number means at the minute. However, I just want us today to be able to work out these definite integrals. So let's do this question. And really, it's almost like a flow chart. Can you integrate that as it stands? No. Why not? It's a fraction. So we're going to integrate and we're going to sort it out so it's not a fraction. So I'm going to simply say, and it's a common thing you'll notice, this has cropped up before, x squared divided by the square root of x is x to the power of 3 over 2 plus 2 x to the minus half dx with respect to x. That simply means you're integrating with respect to x. It's a very good habit to get into for next year. Now we integrate. Now, very common errors here. Again, the fractions, we don't like fractions, you never have. Well, increase the power by 1, x to the power of 5 over 2, and then divide by 5 over 2. Well, to divide by 5 over 2, you multiply by 2 over 5. So it's 2 over 5. Yes? Plus, now then, x to the power of a half minus half becomes x to the power of a half. And then you divide the coefficient by the new power. Well, the coefficient was 2. 2 divided by a half is 4. So now we have integrated. Okay? Plus c, of course. And then we put that in square brackets. And then we say, but we haven't done the substituting yet, which is 4 and 1. Okay? Now, simply from there, we substitute x equals 4 into this, minus substitute x equals 1 into it. There's lots of substituting going on. Effectively, any A-level maths has finished here, because the A-level maths.
Mr. Bentley, we can't hear you again. Oh, and we've lost your camera apparently as well.
Can you hear me now?
Yeah, all fine now.
Yeah, I just unplugged it, so right. Sorry about that. So, had I just gone off then, Dr. Evans?
Yes, very seconds ago.
So, as I was just saying, whether you heard me or not, the A-level maths is finished at this line. The rest is just by being careful. But it's a theme I keep saying to you. Losing marks because of careless slips. You might think, oh, I knew what I was doing. Yeah, but the mark you lost is still a mark. So we don't want to lose those marks. So here's how I would set it out. 2/5. Now it's 4 to the power of 5 over 2. In other words, the square root of 4 to the power of 5. So I would write times the square root of 4 to the power of 5. Okay? Plus 4 times the square root of 4. Plus c. Minus. And now I'm going to put 1 in there. So it's 2/5. Now 1 to any power is 1. So I can just put 2/5. Plus 4, square root of 1 is 1, is 4, plus c. So what's happened there is, the 4 is in that.
Mr. Bentley, we've lost you again. We've lost your sound. And your camera.
Am I back with noise?
You are back, yeah.
Sorry about this. I'll try not to touch it at all. So, really, on your calculator, work that out, and it works out at 104 over 5. So 104 over 5 plus c minus 22 over 5 plus c. Now you will notice that the plus c and minus c, the c will always disappear. So you'll in fact get 82 over 5 plus c minus c. which comes out at 82/5. So what that means, of course, is because in every case the constant will disappear, we say, you know what, we're not going to put it in. We never put the constants in with the definite integral because we know they're going to disappear. So as soon as you see limits there, that's what they call limits, when you integrate, do not put the constants in. Now, there are another 3 pages on integration. But what I didn't want to do, and I've made an absolute conscious decision on this, is to rush through it so that you don't understand it. It is worth investing a good hour on integration to make sure you can do it, because you will have done that much differentiation from first principles, turning points, maximum, minimums, all the things, sketching graphs, we use it an awful lot, and then your teacher will say, right, integration, 2 lessons, bang. But you know what? It's as important as differentiation. So I'm going to have Mrs. Evans as help now. I'm going to lose the camera for a minute, and I'm going to show you what what you will be available for you later. So if you just bear with us a second, I'm going to do that. Stop sharing, and if Mrs. Evans can, let me share that.
Yeah, it's up.
Right, now, this is one of the documents is called Integration Practice, right? I'll talk you through what you should do before next week. It's certainly not every single question. It's not very high-tech, but as you probably gathered, I'm not high-tech. Question 1, the indefinite integral, right? So you're going from the differential, which is there, back to the function. Integrate. Okay? Now then, exercise 1.3, you're now given a point on the curve so you can find the C in each case. That's exercise 1.3, right? Do not do every single question, for goodness sake. You haven't got time, life's too short. And exercise 2.1, right, is find the exact values of the following definite integrals. And it's not copied brilliantly, but it is readable on mine. You won't read it on the phone, but you would read it on... one thing that used to get me was, which way around do you do it? Well, it's always top minus bottom, top minus bottom, top minus bottom. Okay? Now, as well as the answers, the questions there, the last page of this document, I've photocopied the answers, so you can check your working, okay? And if you've got any issues from that at the start of the lesson next week, when we finish off integration, you could ask them. Now, this does mean, of course, we're not going to have very long for trigonometry. But I just thought, you know what? I would much rather you got integration, got it nailed, because there's so much work on integration next year. Pretty much the calculus will go from the loading it was this year to as much integration as was differentiation. Okay? And that is 6 o'clock. So we will finish off integration next week. It's not one of these empty promises. It will be done. If you've got any comments, please make them before you leave. Otherwise, thank you for listening.